So last week we did an experiment with the modified Atwood machine, which is special because it's not an Atwood machine, but that's okay. So hold on, I'm setting my pens. So I'm going to kind of fill you guys in on some of the details about that experiment so that you're aware of them, because we're going to talk about the Atwood machine in the future, and then this way you'll know. I think it's kind of mean to like start throwing in problems about it without you guys having actually experienced one. I feel like it's not cool.
Dr. Mary?
I know, right? Okay, so this is stuff that you can write in your notebook right alongside the experiment, so you have it for the future. So with our modified Atwood machine, we had a car that was sitting up on a table, and then we moved our car by hanging some mass off the side of the table and pulling on it. Right? So far, so good. So one of the things to do when we're thinking about why things are working the way that they are is to make a force diagram for them.
Is Jack Hammer online? Is he present online?
Yes, he is.
Thank you.
Oh no, she's mad at me. Okay. I'm trying. Sorry, I hurt my neck last night. We did teachers got our COVID vaccinations on Saturday, which was fine, except I was tired yesterday. Like I was in bed so long that it occurred to me I should probably get up when I heard my kid say, "Is mom even home today?" And then like during the halftime show, I'm sitting on the couch and like falling asleep. And I told my husband, I was like, I'm going to bed before I fall asleep here. It's like 8. Yeah. Well.
That was one of the worst games I've ever seen in my life. That was so boring.
Okay, so if we're gonna draw force diagrams about what's happening here, the first one to consider is the cart. So what is the cart experiencing? Well, with the cart, we've got a normal force upward from the table. We've got gravity downward, and it's going to be pulled to the side, right? Force pull. So we've got that going on.
Should we just add these on like the bottom of our notes from the lab?
Yeah, wherever it makes sense. That's fine. You can go to the next page if you want to. I've got a plan for this already, so it'll be pretty neat. And then we've also got our hanging mass off to the side. I'm going to draw him down here. And our hanging mass has gravity, and then there's some tension on that string, right? Because I can imagine that there is our string that's attaching these two force diagrams together. So far, so good. Now, question is, do we have any Newton's third law pairs here? Remember, Newton's third law says for every action, there's an equal and opposite reaction. So one thing too about Newton's third law is that they have to be two forces that are happening on two different objects. So if we take a look at these, we're saying that because they are balanced, normal force and gravity on the cart are the same magnitude, and tension and gravity on the hanging mass should both be equal. But that's because we think that they're balanced, right? So maybe I don't know, maybe these aren't equal. Actually, these probably aren't equal. But what is equal is the pull on the cart from the hanging mass and the tension on the hanging mass from the cart. So these two guys are actually going to be a Newton's third law pair. This one and this one.
How can they be a Newton's third law pair?
Isn't that interesting? Because they're not, are they? They're in different directions.
Well, I guess if it's like, yeah, no.
So is it possible for us to put them in the same axis? Yeah, we could. So we can change the way that we look at this problem. We can put our cart, I'm just going to redraw it. Gravity, normal force, that pull. And then here's my string. Only now I want my hanging mass to be in the same axis. there's tension, there's my hanging mass, and there's gravity on the hanging mass. This one is the same. So I just rotated it. How do you guys feel about that? Does it bother you? This is why just throwing out Atwood's machine problems is kind of mean.
So it doesn't like matter if you which way you change it, as long as like the pairs are still the same.
What do you mean?
Like as long as like force gravity and force tension are both like going opposite of each other. Like you
Force
can
gravity.
flip it upside down.
These two?
force
Yeah, you got to keep them. You got to keep them kind of oriented within that object. But the reason this kind of works is because I know that this pull is pulling my cart to the side, right? And so I'm kind of looking at this from the perspective of the cart. So if my cart says it's going to get pulled to the side by this hanging mass, then that means that the force of the hanging mass are going to be in that same axis. So by having gravity pull downward on the mass, it's indirectly pulling to the side on the cart. Does that part make sense? Okay. One thing we need to pay attention to when we're working in this unit is the idea of net force. And so net force is the sum of all the forces that are along one of the axes. And so here, if I wanted to write net force, I could write that by adding all of these together. The pull plus tension plus gravity on the hanging mass. I also know that my net force, according to Newton's second law, is going to be mass times the acceleration. So this gives me a bunch of variables and a relationship between them. Another thing that we know, what sum would we get if we added the pull and the tension? What does that equal?
Negative gravity.
Yeah. What number would those be though? 0. So adding those two together would give us 0 newtons because those two are balanced. So we can solve for some things here, right? Okay. You guys have any questions so far? All right, so our first experiment. In the first experiment, we changed our hanging mass. So if we're changing the amount of mass that's in our hanging mass, what force are we changing? Which one from our net force equation?
Wait, you change the tension.
Changes the tension? What else does it change? What else does it change?
Gravity.
Yeah. So we're increasing all of these, right? The most important one though is that we're going to change gravity, right? We're going to change the force downward, which is going to cause changes to these other ones. So we changed those. And what I think that you guys got, because I walked around and looked at the data you guys are getting, is that when you change the mass and measure the velocity, you got something that looked like this. Is that what we got? Yeah.
Was this for the first day or the second day?
First day. Sorry, that looks so terrible. Hmm. Experiment. Okay. So what did we call it before when we saw changes in acceleration? Sorry, change of velocity. I gave it away. Okay, so acceleration is when we see a change in velocity, right? So what we found if we added more mass is that our average velocity, because since you were looking at the time over a set distance, this was really average velocity. And this mass was really Fg on the hanging mass. So if we change the gravity, we were changing the average velocity, and that was doing something about how much we were accelerating. Why wasn't the acceleration constant, though? Why didn't we see a constant increase in the velocity? It's kind of related to our shoe lab. You guys remember the shoe lab? So with the shoe lab, everybody took a shoe, and we added mass to the shoe, and then we pulled on it. And what did we find? Yeah, the heavier your shoe was, the more force you had to apply to make it move. And what we were trying to do with our shoe lab was get a coefficient of friction. But the second experiment that we did with our Atwood's machine, so second experiment.
What did you write next to velocity?
Average.
Oh, okay.
Yeah, and it's actually our average velocity because we're not looking at it. We're looking at a single distance and a single time. So in our second experiment, we changed the mass of the car. So think about this in terms of our shoe lab. When we changed the mass of our shoe, it took more force to make it move, right? And so if we were keeping the force constant with our experiment here, if we increase the mass of the car, we would expect it to go slower, right? Is that what you guys found? Is that as you increase the car mass, so as car mass got larger, your velocity, or average velocity, was smaller. So it should be something like this. And why was that happening? What did we not draw in our force diagram? I'm going to copy this force diagram. If our car is going to go slower because we've increased our normal force, why will it not accelerate as quickly anymore? What are we missing? It means we didn't account for something. Yeah, friction. It's like just with our shoe lab, we said it took more force to pull it because there was a relationship between friction and normal force. And so if we increase the mass of our car, we're going to see that it requires more pull to get it going. That's why, how many of you guys had a car that needed more hanging mass because after a while it wouldn't move at all? It was possible to add enough mass to your car that friction was big enough that it was bigger than gravity on the hanging mass. And so you had to make this bigger to overcome that. So
would the friction be on the hanging mass or on the car?
It's gonna be on the car. It's gonna be right there. So in the system, you have to make sure that for the car to move, that the force from gravity on the hanging mass is going to overcome friction. If it doesn't, your car won't move. What questions do you guys have about the experiment? No questions? Okay. Seeing no questions, I'm going to stop recording. And I want to talk about the blue packet. We're going to make sure that our class has no hiccups if we have snow days and weird stuff tomorrow.